I want to thank you, Lucy, and all those who came before me. You guys did a wonderful job of setting up my talk. You saved me a bunch of time and less stress on me. So this is an integrated study between inorganic and organic proxies. And I study other Tim Lyons and Gordon Love. So biomarkers and a lot of proxies is what you're going to see in this talk. So let's get started. You're going to see this huge redox timeline from about 4 billion to the present. First off, the red curve you see is the classic two-step oxygenation event that you know, the 2.4 and around the 0.8 or so. The blue curve is an emerging model that shows that right after the great oxidation event occurred, it dips down to about 10 to the minus 3 PAL and rises again until maybe about 0.9 again. And you can find this on Lyons 2014. I want to highlight that eukaryotes fossils were found at around 1.9, and the rise of animals occurred shortly at around 500 million years ago. Right below that is the classic redox structure of the ocean. For the first 2 billion years, you see that it's an anoxic or ferruginous water column that has free iron in the ocean. And then right below that is actual data collected from shales. And why is this important? It's because life, as we know it, started in the ocean. And studying what the condition of the ocean back then was is really key to unraveling the mysteries of how life evolved out of the ocean. So my study takes place at around 1.5, right after eukaryotes have already emerged, but right before the rise of animal. So the boring billion, what is it? It's a period during Earth's time during the mid-Proterozoic, so about 1.5, and it got its name from very little variation in the delta C13 record. And you just see it flatline for about 1 billion years. And we believe that this is what caused the eukaryote diversification to stagnate. And recent studies have shown that the boring billion is a misnomer. It's not really that boring. Because if you guys recall, there's 2 oxygenation events that flanks both sides of the boring billion. So this implies a very unique ocean chemistry. It's neither anoxic and ferruginous like the Archean, but it's not fully oxic like the Phanerozoic either. So it's somewhere in between. Luckily, most of my data, and in general, because Lucy mentioned that there's a scarcity in the rock record to show where these oceans come from. My rock record comes from the Outreach core, so thank you, Kira, for showing what a core looks like. And this site in northern Australia at the tip was originally surveyed because there were reports of live oil by Jackson. And I'm grateful for that because they did some sedimentological studies and geochemical studies to show that these shales were marine in origin. And paleogeographic data showed that it's a lot more connected to the ocean than the previously studied Barney Creek, where if you guys read any of those papers, that they reported green and purple sulfur bacteria, which is an indication for photic zone eosinea. So eosinea is in anoxic waters with lots of hydrogen sulfide in it. So this will be the only data slide you'll see. Stick with me and I'll guide you through it. On the left is the strat column of my Outreach core. These are all shales, so if you don't see them where they look like sandstone, I apologize, it's just compressed. Right away you notice that they're aligned very nicely. This is organic carbon by weight percent, 2 iron proxies, which is a ratio here, and 2 trace metal proxies, molybdenum and uranium. Overall, they show a very unique pattern. You can see that organic carbon tracks the iron and the metals very well. And every time I meet up with my advisor, he ends the talk with nice data, which is something you want as a grad student for validation. So once organic carbon kicks in at around 700 meters, you see that the iron also rises above this red dashed line that I put in. Now this is the upper limit for a cutoff where oxygen in the water. So data samples that are On the left side of the dashed line is oxic, and data points that lie on the other side is anoxic. Now, these aren't hard cutoffs. It depends on really a lot about your setting, and you need to have context about your geologic rocks so that you can move the bar slightly left or right depending on your settings. Any rocks that are anoxic can also further tell you by the pyrite, iron pyrite to the highly reactive that they're eugenic. So there was a lot of hydrogen sulfide that bound to these rocks, showing that they were a eugenic water column. So these two alone tell you the local water redox, right? Now, what does the trace metal proxy tells you? Intrinsically, they're also local. So if you were to look at molybdenum, you see that it's flatlining at crustal value until you hit the middle Valkyrie, which is around 900 to 700 meters. And then you see that it spikes all the way up to about 115 ppm. Now, this is one of the highest recorded molybdenum concentrations in the mid-Proterozoic. And if you were to read Scott 2008, he would track the molybdenum all the way down to the mid-Proterozoic, and it's actually, these concentrations were higher than his. Uranium also tells the same story. It's independently buried next to molybdenum. See, molybdenum requires hydrogen sulfide to be buried, whereas uranium only requires reducing conditions, which is anoxic, to be buried. So you know that these signals are genuine, and they're not a false positive by maybe the tidal flux. When you combine these trace elements with the iron proxy, you can get a lot of data and even infer global reservoirs. So in the orange box, when you have molybdenum data that is very low in the 20s to 40s, global eugenia is only possible if you have iron proxies that suggest that molybdenum is low, which is here, and the TOC is high, which you see, right? And also when the iron proxies show that it's eugenic. However, that's not the case. And we know that it's not globally eugenic, a Canfield Ocean, if you will, because there were a lot of molybdenum being enriched during this time, and it's eugenic here. So therefore, it's not a global extent. Uranium, on the other hand, just tells you that, yes, this was both also anoxic. So when you develop a paleo-organic proxies like this, you build a backdrop so that you can look for biomarkers a lot easier. And this is one of the first integrated search where I combine inorganic proxies so that I can look for molecular biomarkers a lot easier. I didn't want to bore you guys with boring chromatograms, but I'll tell you that I targeted areas that had high molybdenum because it's an essential nutrient for nitrogen fixation, and areas of high organic carbon just so that animals or fecal pellets were buried there, or just whole panes. And you also want areas that are above and below the eugenic transition so that you can have a comparison. This is one of the very few studies where if you find something, it's fantastic news, but if you don't find anything, that's also good news too, because it's what you predict. So in this case, I wasn't in a losing situation at all. The bottom line was that when I went through all these samples, about 120, I don't really see any detectable styrene. So styrene is a cholesterol that is for a biomarker signature for eukaryotes. And you just don't see them in these shells. So to sum it up, the evolution of the atmosphere and the ocean is a lot more complicated than originally theorized, and that makes sense. Long-lived geochemical stability of the boring billion, the flat line delta C13. Australia has some of the best data in the world. It's really a great place for a geologist.